Okay. This is great. This is a really new pointing stick. So this is a, that's not what we want to talk about. We want to talk about this. Okay. All right, we started on Simon's model at the end of the last lecture, when you were just feeling the energy coming to your bodies, you know, really strong, the last 15 minutes. So yeah, fight the sleep. Okay, so I know, 1 o'clock, right? Optimal sleep time, yeah. I sympathize. The first time I ever fell asleep in a lecture, because I used to get up at like 5 to do a paper round of all things. So eventually it got to me. But the thing was, it was a lecture hall and it was all banked, except there was a comfy chair. There was an actual armchair here in the corner. And I came in late. I was the last person. I sat in it, gone, you know. Woke up drooling on myself, so. Yeah, so I have sympathy. There was also one time where a professor got right in my face. Beard, spit everywhere. There's this crazy guy, Norm Frankel, actually an American guy. He went to MIT as a kid, and he ended up in Melbourne in Australia. But yeah, he used to bring his dog in. He had this big German Shepherd that would sit there. He had big cowboy boot things on, which kind of caved in like this, and big belly, suspenders, and would just yell about quantum mechanics. Anyway, it was pretty great. But occasionally he would spit at you, and you get chalk and some parts of Norm Frankel in your face. He's a great guy. Mildly intimidating. Okay, so this is these. Let me see. So I've added some postcards. This little guy is emblematic of what we're traveling through right now. So it's a growth story, and we're going to get our power law size distribution out. And these are little power law things growing. That's actually how they will grow. They get longer like this. So this is the Simon model story. So we're going to actually go through the mechanics of this. We had a nice setup for it. So let me quickly get back to that. Okay, I can jump through. Well, we'll come back to the history of it, but we know it started 100 years ago, almost. And this was the basic idea, all right, just to get it again. So we start with one thing, whatever it is. You know, we could be talking about words or cities. You know, one person says, I'm going to make a city. And at time t equals 1, so obviously this is not really how things happen, but it's a very good parsimonious model from which we could build out. Again, this is Herbert Simon's model. So we have a clock running, and a new elephant appears at each time step, so it's a brand new one. And two things can happen. It could be a mutation or innovation, right? So that happens with probably row, so it's a new flavor. It would be a new city, if you like, or a new word that hasn't appeared before. Or it could be a copy of one that's already been around. So in case of elephants, it's the same color as an elephant that exists, and it's randomly chosen, right? If it's cities, you're randomly choosing from all the people who live in these cities. You're just choosing one of the people and then going to live next to them. You're not choosing from the city, so that's an important distinction. We talked about this, right? So it's not group selection, it's individual selection, which then turns into a kind of group selection, right? So the bigger your group, the bigger the group of animals, elephants, if you like, that have the same color, the more likely that you will pick one of them, right? And it's linearly proportional, of course, to their size. Okay, so we set this up, and the next thing was to go to the analysis, which may or may not work when I click this button. Oh, I don't know why the little, come on. Can you see it on that? It seems to just lose its ability to be around. All right. Okay. Bad thing. Oh, okay. Now, who's behind Adobe? It's a faceless organization. I can't yell at anyone. I'm not a yeller. Okay. So analysis. All right. So let's see. So did we get to this? Yeah. The last thing we talked about was, well, all these different things we could add to it. And I'm sure you could think of many, many more, right? Elephants could disappear, they could move, they could change color, right? It means you could move between cities, or a word ridiculously would change to another word in a book. You can think about word usage in language, of course. And you could change the way that things are introduced, which is certainly true of language and books, and that's a that's an aspect here that's not correct, apart from the whole random writing of books, but that's one we can point to as well. And different selections based on group size. So you could have the rich gets very much richer and the rich gets just a bit richer. You could have other things like that. Okay, so let's go through an analysis. Right, we'll figure it out to some extent. I'll give you some space to enjoy calculating things on your own, or in teams. We're humans. All right, so we'll do that. Then we'll look at a couple of examples actually from Simon's original paper. It's a great paper. You really should read it. I mean, it's 1955, but he just, destroyed it. And we'll look at some of his examples. And then we'll have this piece about catchphrases, right? So what people have called this mechanism. So rich gets richer is sort of, I think, probably the most clear one. But you'll see that people have chosen different framings. All right, so let's, and then we'll get on to Mandelbrot's approach. Okay, so the big deal is this is a random growth model. This is an optimization model. And they're both obviously sort of wrong. It's some mixture of them perhaps, but there's some aspects of Simon's model that we'll see are really clean. All right, so at some point in time we end up with I groups, or sorry, some number of groups, and we figured out the other day that would be quite simply, right? The innovation rate is rho, then roughly rho times t equals the number of groups at time t. You could think of it as the size of the vocabulary, right? So if you just have a dictionary, you just have the enters once, of course. So you can think of vocabulary, number of cities. And they have different sizes. So I'll try to keep using the ridiculous elephant example, the city example, and the word example. All right, fine, good. So K is going to be the size of the ith group. Then we'll say, okay, let's count how many groups have that same size. So this will become our crucial thing we're trying to solve for. Right? So you can imagine after a while, there'll be a lot of groups of size 1. So these new elephants appear. A lot of them are assimilating, they're copying someone. But there are these new ones appearing, but there's only one of them, right? So if you've got 10 million elephants, the next elephant appears and it's new, right? It's a kind of a pale chartreuse. Then its chance of being copied in the next round is pretty low, right? So there's certainly this first mover advantage is another term here. Early on helps, appearing early on helps tremendously. So you can imagine there'll be a lot of these elephants there's only one of them, they're unique, or words that appear only once, and we'll figure out how many of those there are. So with Hapax legomena was this term. So there's that. And cities, where just one person lives. So we'll call it a city. So that means you're out in the woods by yourself, sending packages to people you don't like. Okay, those kinds. No, it's okay. It's okay to live in the woods. All right, so, okay, so how does this thing evolve over time? Right, so this is a dynamical system. The very important aspect of this is, we're looking at how this thing becomes something, how it grows, right? That's a big feature of, as I said the other day, our scientific descriptions. Okay, so let's get a handle on some of these things that we can do, especially in this very simple model. So this sum has to equal t, right? So this is the number of groups that are of size k at time t, and if you multiply that by k, then you get the number of individuals that are in groups of size k, irrespective of their type. And then if we sum over k, then we have to get the total number of individuals that are in the set so far, and we've just made it a clock, so it's t. So that simplifies things. This should look like a mean. This is a mean, right? So if you imagine this is normalized properly, it's just a count at the moment. This is normalized properly, it becomes a probability distribution. So so the average degree, or degree comes later. Average size, normalized in the right way, is proportional to t. Okay, so that's good. That's going to help. We want to talk about probabilities eventually. So we want to get to we'll have our herd of elephants, or our distribution of cities, or our book, and then we're going to randomly choose one elephant, or randomly choose one word. Or we might randomly choose a city. Sorry, what did I say? We could randomly choose a city, or we could randomly choose an individual, these sorts of things. Okay, so this is going to be the case where we choose an individual and then we look at the size of the group it's part of. Good, so let's concentrate. Let's get into our brains. I have to think, it's unfortunate. Okay, we have this. This is our definition. So, and we just sort of saw this in the previous thing. So this is how many elephants live in a size k group, right? So k times the number of groups of size k. And there are t elephants overall. So it should be this guy divided by this guy, right? These are the number of, the little quantity is the number of elephants that live in groups of size k, however many there are. And t is the total number of elephants. So this quantity divided by this quantity gives us our beast. Okay, so that's our result. Right? So now, this is something that's evolving. You know, we kind of want something asymptotic here. We want this thing to sort of fill in to be some kind of nice piece that we can handle. It's not always the case. Certainly if you change the model a little bit, you can end up in all sorts of trouble. Mathematical complications. We'll get to those later on, maybe. Okay, so is that reasonable? So this is just connecting a count to a probability. Of course, we have no idea what this count is. You know, K is good, T, these are good things, these are all solid. This is a guy we have to figure out. Exciting, right? Very exciting. Yeah. There should be a drum thing in the background. Okay. Maybe not. Okay, so let's see. So that's a comma, actually, not a prime. So, okay, so how are things going to change? So we want to look at how this number evolves. And there are two ways for this to happen. So the number of groups of size k could go down one if you have an elephant that's in a group of size k, if it's replicated. Right? So the new elephant appears, a new elephant appears, and it copies one in here. I really want to draw an elephant. Okay, so your new elephant appears, and it's got some ears. Okay, so this guy appears and copies someone in here. So then this one goes to from k to k plus 1. So now the count of groups of size k goes down 1. The groups of size k plus 1 goes up. On the other hand, we could be down a step below. Our elephant could go to a group of size k minus 1. That group now becomes a size k. So we get a plus 1 in that case. All right, so here are the two pieces. So the number of groups of size k goes down 1 at time, so it's t plus 1 here, t plus 1. And this happens with this probability. First, let's put these pieces together. There's a probability 1 minus rho that you've chosen to replicate. I have to maybe say that again, right? So there's rho and 1 minus rho. Rho was a probability that your new elephant is an entirely different color, or a new word is an entirely different word, or your person goes out and says, I'm going to live in Minnesota because these summers are so nice, and makes a house, right? So that's rho, it's the innovation rate. So 1 minus rho is your copying, or you're going to live in a city that already exists. And then we have, this is the probability that you choose, once you've done that, the probability that you choose a group of size, an elephant that is in a group of size k. Right? Once again, we're not choosing the group, we're choosing, there are all these elephants in here eating approximately 200 kilograms of food a day, I think. Anyway, they do. Oh no, they eat about 100 and they destroy about 100. Okay, something like that. About the same as a human. Okay, so let's see. So you're choosing one of these characters, that's right. Right. And that's what this probability is here. On the other hand, your number of groups of size k can go up 1, and that happens with a similar looking probability, but let's see what the change is. So again, you have to have thrown some funny looking die that said, okay, you're going to replicate. So you replicate, and then you have to choose an elephant that lives in a group of size k minus 1. So everything's down a little bit, k to k minus 1. That's k to k minus 1 and k to k minus 1 here. Is that okay? And the normalization again is t, right? That's the number of total number of elephants, just because we made it a really simple game. So we're going to put these things together. There's some master's equations is the term that we use for these things, various other pieces. We're going to do some, so how is this? How are we doing? How are we doing? Horrible? This is all accurate right here, right? But we're saying, the chance of any, once it gets big enough as well, the chance that any particular elephant is chosen is 1/t, right? So it's going down and down and down. The groups that are big have a better chance. But this is all talking about just one more elephant. Now we're going to have to smooth this out a little bit to turn it into something we can solve mathematically. So we'll do that. So there is a special case for this elephant if it chooses a new flavor, right? So we have to write down that equation. So that can happen. So we can have it's a new flavor like this, or so this is N1T, right? So this is the number of groups of size 1. The number of groups of size 1 will change if your new elephant or your new person moves to a city and creates a city, or it's a totally new word. Then you get one more here. But you lose one if one of these unique groups with a unique individual gets replicated. Okay, so that's going to work like this. Simple, and this is the one that really changes. So number of groups of time 1 goes to just the same as you had before, plus 1. That happens simply with probability rho. That's it. Well, it's a completely new flavor. It happens with probability rho. On the other hand, so that's all of what rho does. So if the rho probability, that's exactly what happens there. You lose 1 from that count of groups of size 1. Well, first of all, in this case, so you have to have 1 minus rho. You have to have the probability that you have to have replicated. That happens with probably 1 minus rho. And then this is n1 divided by t. So this is the number of groups of size 1, which is, so this is 1 times n1, right? We had pk of t was equal to, or is equal to nk of t over t, but it's got a k here. So in the case of k equals 1, there's 1, 1, and t. So that 1 has disappeared. But this is really the same equation as before. It's exactly the same. Well, let me use this one. Same as this one, put a 1 here and a 1 here. Okay? Okay, so that's a separate little bit. Everything else is, once we're k greater than 1, we have an equation we can just use in general. So we'll have a little kind of n cap to deal with. Yes. Let's put it all together. So we have these pieces. This is expectation. So on average, we expect this to happen, right? So these are probabilities here. So, right, we were talking about the weight of them. So there's really okay, so it's here. There's a plus 1 here, and I could fix that. There's a plus 1 there and a minus 1. I could make this more clear. Okay, 1 minus rho is the probability that you're replicating, and then you have a plus 1 and a minus 1 associated with their probabilities, right? So here's the magnitude of the change. So plus 1, right, it goes up. If a group of size k minus 1 gets replicated, you get a replication in there, and you lose 1 here. Okay, so that's what you expect on average. I mean, in reality, it's either plus 1, minus 1, or 0. Nothing happens. Most of the time, nothing happens once it's big enough. You get a plus 1, a minus 1. So there's also a plus 0 times the probability that nothing affects you. So that's on average. For k equals 1, we have a slight change. So this is the number of groups of size 1 at time t plus 1 minus the number of groups of size 1 at time t. The expected change for them is putting these two pieces together. So rho, this is a plus 1 times rho. That's probably you get 1 more. And then a minus 1 times the probability that a unique individual was replicated, found a friend. So we can leave this one aside. We'll come back to that one later on. This one is one we're going to have to deal with. And as I said, in reality, if you make this algorithmically, what's happening is you're getting a +1 or a -1 or a 0. What we're going to say is, well, let's sort of imagine this runs for a long time, and over enough time, you're going to get a little bit of this. If you could think of it like this. Eventually, you will get a +1, or you will get a -1. But on average, this is the way things are changing. So if you let the thing run for long enough time, we're just going to drop these guys, and we're going to turn it into eventually we'll turn it into a difference equation. You can turn it into a derivative as well. There are different ways to do this. We say this is so there's a rate at which it's changing. So these things become fractional, which is obviously naughty of us, but it's enough to sort of smooth the story out and get it to work. And you can check that it's okay later on. That's not a bad thing to do in math. Do something dangerous and then check that it was okay. No one was hurt. All right, so we're going to do a couple of pieces. As I said, we're going to drop the expectations and kind of imagine that this is the general story for how this thing is changing. And we're going to assume that eventually this distribution is going to stabilize. And you can check again to see later on if that's true. Right, so first of all, you make this assumption, you see if it works. Do you get a reasonable answer? It could be, for example, that the distribution is just falling apart, right? It's just that you end up with a spike. There's one winner, and then it's never really settling down. That group is just getting bigger and bigger and bigger, so it doesn't become stable. We'll see that for all rho not equal to 0 or 1, those n cases, this works. But the idea is, okay, what we're going to say is the number of groups of size k is just some quantity that's fixed times t. They're all just growing gradually. All right, we'll drop those expectations, the averaging. This is a little scary, but the number of elephants is now fractional. But it's okay over large enough timescales. A little bit rough there. That's the sort of thing that mathematicians will worry about. Okay. So later on we'll come to this. This is a nice little piece. But now we've just introduced this small n here, so we might as well play around with it. So we had this before. So the number of groups that have size k. Okay, so we have the number of groups of size k. That's this piece. The total number of groups was rho times t, right? Okay, so we can do that. So we have rho times t. We're going to replace it by this stabilized structure, nk times t. The t's cancel, so we just get this nice little beast here. We'll get to that later on. But this is, what's the fraction of groups that have size 1? What's the fraction of groups that have size 2? So if you look in your dictionary, what fraction of the words appear once? And typically it's about half. If you create a dictionary for a text, for example, or a lexicon, it's about half of them. It's a lot of them. A lot of the words do only appear, once. So that gives you a feel for it. The words that appear twice is about a sixth of them. A sixth of the individual words appear twice only. So there's a lot of very specialized words. There was a piece I tweeted the other day, just from. I guess I retweeted myself. I do that, and it is a little disturbing. Your phone tells you that you retweeted yourself like 4 times. Which was it's a piece on language log, which is a sort of great blog associated with linguistics. Lots of good people write on it, and it was something I mentioned the other day when we were talking about ZIF, but it was the tension between the encoding and the decoding side of things. I know there was one favorite. Yeah, and the claim is an interesting claim. So the claim is that English in particular, it was English versus Chinese, Japanese, the Korean, right? So that the English, or maybe it's the American version, is structured so that you, as a writer, it's a writer-responsible language was the term I think they used, writer-responsible. So that, you have to explain what you're talking about. You have to make it clear from that point of view. Whereas the Asian language are reader responsible, so there's more interpretation expected out of the. Now, I don't know if it's true, but it's an interesting long debate. There's some good comments. It's there on the Twitter feed. So that the Asian languages are more reader responsible. There's more onus on you as a reader to know what's going on. There's more ambiguity and so on. And this can cause some confusion as people move between the languages. Okay. All right, okay. So here's our sneaky thing. Anyway, I'm just throwing that. That was interesting. We have, what else is in here? Well, I guess my brain went into that because it's this tension between how many words appear once and how many, it's this idea of the tools that these words kind of can be thought of as. Okay, right. So we had this equation in general for n, the number of groups of size k. It's going to simplify because we have lots of cleaning up. Okay, so we're going to take this average away and just say this is how it's changing. And we're going to replace all the capital NKs with nk times t plus 1. So these are subscripts here. Now this is actually just multiplied by t. It's not a function, right? This is multiplied by t plus 1. This is multiplied by t, and there's an nk minus 1 times t here, and a times t here. So these things now come, if you look at this a little bit, you've got t sitting here. Rho is just a parameter, and then you've got your nks. So the little nks are there. There's a little nk and a little nk minus 1. So this becomes it's a difference equation. If we can express little nk as a function of little nk minus 1, we might hope to solve it. T could appear. It's getting exciting. T could appear. Well, we'll see what happens to t. All right, so we're going to move some things around. We want this little beast over here. This is minus k nkt over t. We're going to deliver this to the left-hand side. Do I do that? No, I'm not doing it yet. I want to do that. Okay, all right, we've got these guys to put together. There's an nk here and an nk here. So we're just going to add them together. It's t plus 1 minus t. That's this beast. So these things cancel. So it's just nk. Let's, we can't combine these guys. These are nk minus 1 and nk. But the t's cancel now. So that simplifies. So all the t's have disappeared. So inspired, we push on, right? Many monks have died to get here. So that's why there's actually a bridge, and there's like signs that say you should go that way. So that's why we're here. But it's very nice. This is just nk times 1, so this simplifies completely. And over on this side, we have just k minus 1 times nk minus 1, and this is just minus k and k. So you can see we can bring this beast over here, getting very close. That's what we're going to do. Right, 1 minus rho times this minus k over here. This is just some algebra. We're going to grab it and put it on the left-hand side. So it was a minus, let's say it was a minus sign here, so it becomes plus. Right, so there was 1 plus 1 minus rho times k. And then whatever was left on the other side, multiplying nk minus 1. So now we have nk times a blob equals a blob times nk minus 1. Different blob. So that's good. That's very good. Magical. And the k's are in there as well, so that makes it a little more complicated. Right? If these were just numbers, then we'd have an exponential kind of story, but something's going to happen. Okay. If you rebalance that thing, I think we can do this. I'm just going to take all of this stuff and put it down here, and then rearrange it a little bit. And we'll put the nk minus 1 over here. So this is the ratio, or you could put it over here and think of this as how it grows or decays. And in this case, it's decay, because with the number of groups, as you go up in k, they become smaller, right? The larger group, there are fewer of the larger groups. They're bigger, of course, but there are fewer of them. Good. Good. And let's see, you can think, what happens as k goes to infinity? So k goes to infinity, this bit dominates, this bit dominates. What happens to that? You have to be careful with this sort of badness. What's this ratio? Yeah, what's this ratio tend toward? This is just a little side thing. Okay, what's the limit of this thing? K minus 1, 1 minus rho, 1 plus 1 minus rho times k. What's a nice thing to do to this to make it easier to figure out? "73 monks died, but the 74th one does something else." What do they do? So L'Hopital's is always the goodness. Yeah, right. I think we can get away with not doing it. L'Hopital is great. You've got it in your pocket. It's good. One thing you might do naively is say, well, this is k going to infinity, so these two kind of eventually just dominate and they cancel. But it's nice to make it a little cleaner for ourselves. We divide through. So what I'm going to do is just, certainly it's infinity over infinity, so it would work. Let me just divide through by k, top and bottom. Then this usually makes things very clear for a start. All right, so now you can see that these guys are really going to 0. They're really going to 0. It's well behaved. You don't have to quite, you can put the L'Hopital back down on the table. 1 minus rho over 1 minus rho. So it equals 1. So actually, that's, did I get that right? That's weird, right? It's not really changing eventually. So that seems a little strange. You have to be a little more careful than that. So that's the first order approximation. What you really need to do is you need to go to something plus something times 1 over k plus something times 1 over k squared. You need to think about this a little bit better. All right? So this is a not quite. All right. That'll be a problem to play around with. Okay. So you can solve this exactly. You can solve it exactly in the sense you get n1, n2, n3, n4, n5, right? You get it exactly. You don't just get the asymptotic behavior. You can do that as well separately, but that's what we'll do. Right. So you have to be the 75th monk. 74th monk also died. Okay. So there's this one example where you solve it exactly, and then there's another one which you can just sort of get at the tail without. It's a little sneakier, but you don't have to pull out gamma functions, for example. But you want to pull out gamma functions because they're awesome, so you will do that. So there are two questions associated with that. So one is the sort of the back of the envelope, perilous back of the envelope, and then this is one where you actually go through. There's a tiny error in the Simon paper, nothing of note, but if you tried to repeat the whole thing exactly, there's just a little thing missing somewhere. It's tiny. It disappears, of course. It was an accident. Okay, so you will find this. This is one way to do it. You might end up with this. I'll change that. Make it clear. Right, the exciting business. So if you do this expansion correctly, you'll actually get to this. 1 minus 1 over k to this power. You can sneakily get to this. So here's our innovation rate sitting in here. That's interesting. Let's see, we can tune this up a little bit. So there's k minus 1 over k. So from that you can see that roughly that this is nk is behaving like this piece. This is nk minus 1 is behaving like this piece. So this is a very rough argument, but you'll get to that. K minus this blob, so it's k minus gamma. So in fact, we get the result we're aspiring to, right? So that, well, thinking it should work in this way, that there's a power law decay, super excitement, from a it's a growth model. That's important. That's a really important thing. It's a growth model. There's a power law decay in here, and it's connected to the innovation rate in a very clear, simple way. So 2 minus rho over 1 minus rho, you could write that as 1 plus 1 over 1 minus rho. So we'll think about what happens in the limits as rho approaches 0 and 1. But this is exactly getting this result. So this, regardless of how well it applies to actual language or actual elephants or imaginary elephants or actual, so it works beautifully for imaginary ones, but actual cities, this mathematically works very cleanly. And it does the right thing, which it connects a microscopic or parameter, the rho piece, with a big picture aspect. So gamma is a big picture piece here. It's, this is whether this thing is a gamma equals 2.5 or a gamma equals 2 or a gamma equals 3, those things that make huge differences, right, in how it behaves. If for some reason it's gamma equals 4, then you have a finite, a small variance and a small mean relatively, no surprises. So that's all governed by rho, right? So gamma is governed, if you like, by your innovation rate. Really nice. So we can write it like this, 1 plus 1 over 1 minus rho. And so you can reflect on this a little bit and think about what happens as rho goes to 0. I guess I have it on the following slides, but if you just look at it, rho goes to 0. And if you do 0 or 1, you have to redo the whole calculation because we did some things that won't work. But as it goes, this tends towards 2, which is a bad kind of power law, right? That's one where the variance is very large, is infinite, and the mean is on the edge of being infinite as well. So it's a low innovation rate. That means you're moving, so it should make sense, you're moving, the new individuals are copying a lot. They're moving to the same cities that already, the cities that already exist. They're repeating the words that already exist, so that the rich gets richer part is magnified. Still a linear rich gets rich story, but the chances of being replicated are increased, very simply. And as rho goes to 1, so you're making a new city all the time. Now you've got, right, you don't have any big cities anymore. You can see you do get the odd limit of, as rho goes to 1, this thing goes towards infinity. So you actually get every power law exponent between 2 and infinity. And infinity is kind of a weird thing, but it's basically what is happening in that limit is it turns into a delta function, because when the innovation rate is zilch, everyone moves to a new place, or every word is different, or every elephant has its own color, right? So that distribution is n1 is equal to, well, if it's normalized, the probability of having a group of size 1 is 1. Everyone is in a group of size 1. All right, so really spectacularly, first of all, the connection between the micro kind of, or the mechanism and this overall description is quite spectacular, and it gives us this big sweeping range of outcomes. So it tells you, and we'll use this, I've mentioned it before, but the word universality, it says that there isn't, at least for this mechanism, it depends very clearly, very subtly, right? So you change the innovation rate, it's going to move it into a different universality class. So it's not as if gamma equals 3 all the time. Like you could vary the innovation rate and the mechanism just pushes all that out of the way and gets you back to gamma equals 3. Here it depends sensitively on it. There's a linear there's a one-to-one relationship. All right, so I've said these things. We get between 2 and infinity for 0 to 1 for the innovation rate. So these are just saying these things again. Let's see if I miss anything. Right, so we have a wild power law size distribution, right? It really is a distribution of surprise. For rho equals 1, everything's the same. So it's a tunable mechanism. And now you have a family of universality classes. If you believe that your system was produced exactly by this mechanism, which you'd have to figure out, then you should be able to measure the innovation rate, historically, and measure the exponent and see that those things match up. And so you can do that. The Linux kernel example I mentioned, which seems like a kind of slightly obscure, bizarre one, but it's something that's got fantastic data associated with it. So. And when we get to cities and words, and so there's more complications involved with that. Migration has lots of interesting behaviors. But again, papers keep appearing in Science and Nature trying to explain, say, migration in this universal, general way. We can touch on one of those later on. Yes. It's a kind of a set of projects you can work on. All right. Let's connect this to Zipf's law. So this was the size frequency distribution, right? So I'm going to sample from this thing. What's the probability that I get a word that appears with some frequency we're using twice, with some abundance? What's the probability that we get we're in a city of a certain size, etc. way back last week, I guess, we connected Zipf's law to this size frequency distribution. Zipf's law, so the size of so we rank them, right? That's in your assignment, I think. So you rank cities, the biggest city to the smallest one, the word that appears the most, the words that appear the least. You rank them, and you look at this, and you see these. You see another power law, decaying power law, and so this is the Zipf approach. R to the minus alpha was how we expressed that, and the connection between them using the complementary cumulative distribution function is that this exponent alpha is 1 over gamma minus 1, where gamma again is the size frequency distribution exponent. Let's see. So one simple thing we said: gamma corresponds to alpha equals 1. As we increase gamma, alpha goes down. So that's our story. Yeah. Yeah, it's an elephant group of elephants. You're right. You're right. That's wrong. Yep. Sorry. So like cities, it should be city. You know, it's the size of the city, it's prevalence. You're right. I'll fix that. Thank you. Yes. Yeah, definitely a little bit of a slippery piece here in my brain. Not sure what sort of words are coming out, but I'm trying. Okay, so let's see. Okay, good. All right, so we actually see, this is something we see roughly for a lot of systems. Alpha is close to 1. So it's this scary distribution, right? Very much a statistical surprise situation because it's gamma equals 2. Roughly, there's lots of debates about this, but it's, you know, these are heavy tail distributions. All right, so there's a book, Krugman has a self-organizing economy book. It must have been from, I don't know, can I get this thing? Come on. Oh, I can't see the little mouse. I don't know why that is. Oh, okay. Do that. Yeah, so it's 1995. Okay, that's a while. Let's go back. And I think it's actually where I first read about this. This giant Venezuelan friend of mine handed me the book and said, read it. Okay. So he didn't like it because, as he describes as one of his chapters, because the innovation rate has to be so low to get this exponent alpha equals 1. But actually, it's not so bad. I mean, the exponent is often, a little bit away from 1. It makes sense. There's more complications. So it's okay. It's fine. This was just wanting it to be exactly perfect. I think. All right. Actually, the connection is when I was a graduate student, I wrote to him. He was at MIT for a year, and asked him about this Simon paper, and he wrote back and said, "Here's a citation," which I guess wasn't in the book for some reason. Anyway, very nice. It was good. That is my tiny little interaction with him. I once had a student in this class who said, "Oh, my father employed him." At MIT. So that was different. Let's see. Maybe we're missing some words. Maybe. So you've got to actually eventually get at the mechanism. So you can say, fine, this is great. We've got our, I've measured my exponent. I think this innovation rate is whatever it is. So you actually have to go and measure that. And that's harder to see. If you want to actually get at, well, here's the new thing, it went to this group, and the next one went to this group. There's a lot of smoothing you have to do to see that it is kind of behaving in the way that you want. Because, just one example doesn't help you very much, and there's going to be a lot of fluctuations. All right, let's finish this. We'll move on to the clean it up, because we haven't quite done everything. So we did a bit of a sort of a dirty trick to get to how this tail behaves, but we can solve it exactly. And to do that, we have to look at the end. Okay, one part to clean up. So we had the same story as before. We're going to replace the numbers of groups of size 1, or k in general, by nkt, so it becomes little n1t. So let's do that. We're going to drop the expectations. So there's n1, it's this guy here, times t plus 1, this bit, and this is a little m1 times t. You can see these things are going to clean up. The t's will cancel as they did before, and we'll just get m1 times 1, so that's here. On the right-hand side, we've replaced the capital M1T with just little m1t, so again, these two will cancel. You can see there are no n2s, there are no n0, doesn't make any sense, those things aren't in this anymore. Right, so the other equation, we had nk, we had an nk minus 1, but this is just a row sitting here. So now we can rearrange this little beast. We're going to pull the thing times m1 over on this side, so we're going to have m1 plus 1 times minus rho, so this is going to be a 2 minus rho and a rho, so that's what we end up with, right? n1 equals rho divided by 2 minus rho. Super exciting, all right. So you can think about what happens in these limits. So as the innovation rate goes to 1, it does the right thing. So in the innovation rate, this goes to 1 divided by 1. So that's right, groups, right? This little m1 becomes 1, and multiplying it by t gives you the number of groups of size 1. As rho goes to 0, then this disappears. So relatively few of them will have groups of size 1. But we have to be a little careful. We have to put a t in there. So we'll fix that up. Okay, so that's our story. This is kind of what's happened, right? We've started off with one seed, and it's grown and grown and grown, and new things have appeared. Generally speaking, for these models, the one that's in front tends to get bigger. You can, again, mathematically sort out when that's really true or not. But you know, the ordering doesn't change too much, and it's not a bad assumption to assume that in these perfect idealized models. All right, so that's our little postcard version. All right, let's look at groups. Let's get this right. I put that in a funny place. I didn't mean to put that in. Should be a continuation. All right, so let's see. So the number of groups of size 1, so yes, total, the actual number at time t, we're multiplying it by t here, so we've got rho t over t minus rho. Now, one of the first things we said was the number of distinct groups is rho times t. So we can divide that, we can say, all right, let's see, here are the number of groups of size 1, let's divide by the number of groups of size t, total number of groups. Yep, that's what we're trying to do. So 1 over rho t, total number of groups of size 1. Let's put this in here. So we have rho t, 2 minus rho, that's this piece. These guys cancel, so it's 1 over 2 minus rho. So this thing has a very clean behavior. So as rho goes to 0, right, we get to something, as I said this before, we get to something like a half. So a half of actual groups. For this perfect, this perfect idealized model, a half of the groups will only have one member. And that's not atypical of real phenomena. There are a lot of these little ones, right? There's one Bill Gates, and there's lots of people with not so much. That's sort of the story there. Okay. So as rho goes up, quite reasonably, the fraction increases because you're mutating more and more and more. And you can also, so of course then you can think about what groups of size 2, groups of size 3, you can solve them in this limit of rho going to be a small number. You get about a sixth. So that's not a bad that's a little problem to work out on, to work with. Let's see, so interesting. So this is an interesting aspect of this model. It's a bit unlike, there's a lot of models where you get the tail of the distribution. You show, oh yeah, look, we get a power law decay. This is actually getting the same thing. This is actually kind of getting the small values as well, right? So we figured out what the behavior was for large k, and now we've got the behavior for small k. So that's kind of spectacular. All right, it's pretty good. All right, let's see. So here's this example I wanted to show you from Simon. It's one example. We'll actually look at the early behavior of the web later on from Alta Vista, which was in the days before Google. There were other search engines, which I used to use. So Excite was another one. What else do we have? Trying to remember them now. Oh my God. They were terrible. There were ads everywhere. If you search for fish, it would just give you a page that said fish everywhere. because that was how the search worked, right? It was you did better if you sort of put the word fish invisibly into your metadata, because it's more about the exact content, and Google is all about how things are connected, right? And Google's evolved a lot, but early on it's basically some giant linear algebra expedition, which actually in my linear algebra class we get to that, and also in complex networks, but it changed it completely. I remember a friend coming in saying, hey, try this thing. It's like, whoop, just worked. And then they all went away. Okay, but we'll use data from AltaVista. Let's see. So Simon said, all right, well, let's see how well this works. So here's a reasonable thing to do. You can play around with this yourself. I'll give you Ulysses. What's the rate of innovation? Well, okay, so we'll just say number of unique words divided by the number of all words. That's the estimate. And as I said, we have a student, Jake Williams, who's done all this nice work thinking about actually how this thing decays with time, because it must, right? But, well, it will. So, but we'll just take this as a constant rate of introduction. So if you look at Ulysses, you'll get this roughly. So that's pretty high. There's a 10%. This is much higher than natural, not natural, many others. This is natural.
What do you think the rate of innovation would be for Lincoln's Wake?
Yeah, I don't know. Well, we can. When was it published? Yeah, all right. Look it up. So we can get at these, especially if they're out of copyright. So there you go. That's another assignment question for you. I think so, right? 75 years. It keeps getting stretched. Ooh, that's interesting. Okay, maybe. Yeah. We'll see if you can find a copy. Yeah, so, yeah, or Alice in Wonderland, which is just nuts. Lots of innovation. So, okay, so this is pretty easy to do. You just count the number of, or you, of course, probably in Herbert Simon's case, you force a student to do this. Now we actually force a computer to do it. Eventually, there will be revenge, but yeah. You know this joke, right? A robot walks into a bar. Have you heard this one? I mean, there's a million of these, right? So a robot walks into a bar, and the bartender says, "We don't serve your kind in here." And the robot says, "No, but you will one day." I apologize. All right, so it's not bad. All right. Actually, it's part of a song, and that's where that comes from. All right, so let's see. So this is the real number of, what am I saying, words that appear once in Ulysses. And this is the estimated one using this row. So it's not bad. I mean, definitely close. This is the number of words that appear twice, and this is what you get from that estimate. So these are close to, again, close to sort of a half, using that kind of a half and a sixth bit. Right, not bad. And it's a bit off from a half and a sixth because of this 0.115. That was in the limit, row goes to 0, but roughly. All right, so that's just a little thing to say. It's not bad. All right, and you can look at the exponent and so on. As I said, it turns out to be much more complicated. You've seen with the Google corpus that in fact there's a scaling break, and so this turns out to be universal in large enough corpora, and oh my God, and it turns out to be a beautiful result. It's not perhaps exciting enough for a lot of people, maybe, but there's a scaling break like this. This turns out to be the average text size, roughly. So if you're mixing all these books together, and this sort of thing happens in physical systems all the time, if you're mixing all these books together, then there's an observation now, coming from our group at least, that this is around the average text size. There have been some arguments that there is a core language and a non-core language, which is appealing. That's been around for about 15 years. The idea that there's sort of a set of words that everyone uses generally when they write anything, and then this one has stuff about whales out here, or what's like to live in Siberia. Like there are words that are a little more specific out here. You can imagine that's really more of a blending, right? That there's sort of a backbone of words that people use at all frequencies, and then it starts to become more and more. You throw in the more specific ones that that you won't see in other books at all, right?
Could you just say like the is like the most core of our language though? It's like a gradient.
Yes, right. So that's it. So that's what I'm trying to say. Yeah, exactly. So there's a kind of a core aspect, but then it's not really these two types. So the argument is there's core and non-core. So you can imagine though that it's actually, yeah, exactly, a spectrum. Right. I think that's doable. I think that is adjacent to what we've been doing, and we could sort that out too. Because you can take these two distributions of words, and this isn't done a lot. They may have the same slope and everything, but actually, if you look at the words, of course, there's some different sequence of words. So we do this for our happiness measure thing. We actually kind of take a diff. It's a more, I'm not going to say complicated, but it's a different kind of measurement. But you can see which words are making this score higher than this one, and so on. You should be, and you can do that. I think you can do that. It's not done that much though. Obviously there is this very specific ordering. I mean, there are actual words here. When we do particularly when we do the zip plot, I mean, they're real words. But people tend to think, oh, it's rank 1, 2, 3, 4, 5, and that's sort of the thing. But actually, very interesting. And if this is, if we're talking about ecology, right, this is the most common sparrows, whatever it is, and then, what is it? The hermit thrush is somewhere here, and then we're out to, I don't know, what's getting rare? Phoenixes, that's pretty rare. Although they appear a lot in books, so probably much more than the hermit thrush in a book. Okay, so this is a part that I find quite enjoyable. So everything is fun, but this is a little bit of history of science of how it worked. So great model, by the way, Simon. I mean, like round of applause for Simon. It was very well done. There's an unknown number of graduate students were died in the process, but it's like his paper. I don't know, I guess other people were around, and certainly the ambient idea was around. So we have Yule's paper, this is 1924, and this is going to be about catchphrases. There's not really a catchphrase from Yule, it wasn't the time. We didn't make up a special little thing to sell it and tweet about it and so on. No tweeting. But this was the title, and it's a great start to your title, A Mathematical Theory of Evolution. It's like, yes, and then it's based on the conclusions of Dr. And it just sort of takes a very specific turn at this point. And but it is a model that is, so again, this was for the number of species in a genus. That has, again, this kind of parallel size distribution. That's what the focus was there. Simon's paper has this terrible title, awful title. I mean, you have no idea what's inside it. On a class of skew distribution functions, and amazingly bad. It's just unbelievable. I mean, all right, fine. Skew is also not quite, I mean, skew is kind of like, this is a difficult thing to ski down or something. Like skew is a little bit, right? This is not just skewed. I mean, this is like, absolutely explodingly off to the side. Right, okay. But his introduction is much better, so let's read that. So it's the purpose of this paper, it's not him, it's a paper, it's something outside of him, to analyze a class of distribution functions that appear in a wide range of empirical data. So you're like, okay. And then particularly data describing sociological, biological, and economic phenomena. Not a fan of the Oxford comma. Its appearance is so frequent, noted, and the phenomena so diverse that one is led to conjecture that if these phenomena have any property in common, it can only be a similarity in the structure of the underlying probability mechanisms. That's pretty good. It's not bad. It's good. It's like working for lots of things, and there's some universal piece here, so you feel like, okay, good. Could have worked on the title a little more. Awesome general universal story of everything. Skew distribution functions. Didn't sell it. Anyway, of course it is a very famous paper, so it's all right. All right, so we have those. We had Mandelbrot in there, and we're going to get to Mandelbrot, but he really focuses on language, so he doesn't churn out a great catchphrase. Okay. And Zipf is in here, but Zipf doesn't have a model. Well, I guess I could. It doesn't have his model isn't consistent with the rich gets richer. It's just the humans are lazy. That's it. Okay. No, they're cunning, maybe is the right word, and prone to sloth. Let's see. So the Solar Price, as I said a while back, was the first person to take this Simon's model, or Yule's model. Sometimes it's called the Simon-Yule-Zipf-Mandelbrot distribution. And there's another one. I've got to get that one. Pre-Yule. Sorry. Keep thinking of things. Put it onto a network situation. So a very, really nice piece of work. So it's a citation network of scientific papers. Like we talked about this the other day. Very hard problem back in the day. Now you can create these things. People have had a lot of fun with Archive, for example, the physics archive, ARXIV, if you haven't heard of that. Biology's created one now, I think. But, it was at Los Alamos and kind of made a mess of it and ended up at Cornell. But people put their preprints up there and it's huge. So that's been a really great source for people to play around with. You can actually get the raw LaTeX and all sorts of things, all sorts of stuff you can do with that. So Price noticed this, and he used exactly this model of Simon's to replicate the kinds of patterns he saw in network citations. So again, some papers get tons of citations, and there's this idea of them getting more citations because they simply have citations, right? And
Especially now that Google throws the most cited ones.
Can't help it. So we'll come back to this later on with fame and social contagion and so on. It's really deeply interesting. It's hard to avoid. But in some ways you want a sorting mechanism that does that because you kind of do want to know what that is, but also somehow throws you random things, and some other meaningful kinds of versions of it, because it is a problem. You can see in some systems where you have a top 10 that being 11 is bad. Like there's a real, just getting onto that list is a big help because now you're in front of people's heads. Yeah, right. We can't help ourselves, but it does make it worse. Amazon, they sort of essentially do the same thing. They don't, well, I guess they do rank them by sales, don't they? Number such and such in sales in.
Yeah, they're rated by the different options, but you can also kind of subsidize Amazon to get your products up.
Oh. That's
That's
interesting. So, yeah, we'll say number 4 in whatever, right? That's what they'll do. Yeah, they won't tell you what it's the actual, but they'll give you the ranking. I mean, if you ever want to go and look at the top thing. But because of its recommender system, it is, everyone is, your ability to not copy other people is really diminished. And that's okay. I mean, we are replicators, and it does seem to work pretty well. But it just accentuates the rich gets richer aspect even worse. So Price came up with a term. This is the first time we kind of have a good thing we can put in front of it, cumulative advantage. That's not bad. Right? So you're in front, you get more. Your advantage accumulates. So it's good to be number 1 because your chance of being number 1 remains. It's much more complicated in some fields, tech companies. It's hard to stay number 1 potentially. I mean, we'll see what happens to Google long term, but Yahoo was a big thing. I mean, you can look at all companies in the past that just simply the technology changed, right? So if you were a telegraph operator, you were, killing it for a while, and which bears a lot of resemblance to Twitter actually, because people had to encode things and shrink it because you paid, right? So they put all these interesting little things into tweets, into their telegrams. That happens, and they just disappear. So that's complicated, but certainly not, in academic work, absolutely. Right, okay, so, and there seems to be this, it's roughly proportional to the number of citations. Obviously it's a directed network, there's a big, there's time and the papers are appearing and they can only cite backwards, sort of maybe laterally at the same time. So there are a couple of things he had to do to fix it up analytically. New papers have no citations, so they don't have any size, at least according to this kind of pure model. So the flip was just to sort of put a +1 in there, just to give them all a little bump, so they kind of exist. Selection mechanism is more complicated. The way people are seeing these papers, how are they coming across them? And a lot of that has changed tremendously, of course, because now you don't go into a library and start pulling off journals. You go to a thing, because information lives in infinite dimensional space, really. And so you just, you go to Google and it presents a thing, for better or worse. Less trees die. Okay, so that's not bad, cumulative advantage. Then we have the Matthew effect. This is from Robert Merton, a very famous sociologist. He lived to close to 100, and he was at Columbia. I did see him there at some point. He's again thinking about scientists. It's a good field to study. I mean, artists are another good field to study. There's whole sorts of structures there, and trying to find, what was there anything you could tell about the success. So he showed, and this is not really using these models anymore. He's just come up with a good framing of it. But he did show and argue that statistically, that if you did really well early on, that's good, right? So you have a big hit. You get something in Nature or Science when you're in the early part of your PhD, or even at the end, whatever it is, then that gives you this exposure, and then you have the chance of working in the next place can be a great place. Funding comes to you, students, right? Money. So, and then you get some smart students and they do all the work. Where do you get the Matthew effect? So the Matthew effect comes from the Gospel of Matthew. It's not quite so. The full Matthew effect, I'll tell you what it is. It's not quite what the rich gets richer model is. Okay, so for everyone that hath shall be given. So that's it, right? So fair enough. You've got the hath going on. You'll get some more hathing, right? Is the story. But actually, the full thing is, of course, there's some Aramaic at some point, right? So it's maybe this. But from him that hath not, that also which he seemeth to have shall be taken away. Gets worse, and cast the worthless servant into the outer darkness. There men will weep and gnash their teeth. This is not in the model, but certainly one could add that. I guess it's when people leave academia, which is fair enough. So one of my students suggested this could be a unit of purchasing power, the hath. There's adjacent to this the Matilda effect, which is a bad thing, but it's good that it's been quantified, that women's scientific achievements are often overlooked. It sort of has a parallel thing there. Humans can be bad. All right. Okay. Merton was good at this, actually, the catchphrase thing. So he came up with self-fulfilling prophecy, which, that's impressive. Role model, unintended, which is one of the sort of themes of complexity, or unanticipated consequences. It seems to be attributed to him. Focus group, he called it a focus interview, but the whole concept of a focus group is apparently his, which organizations use all over the place, for sort of better or worse. So he was good at these things. His son won the Nobel Prize in economics in '97. So, not a bad outing for a career. All right, so Matthew effect is used a lot, right? So you'll use that. But they leave out the gnashing of teeth part when they say it. Okay, just to be clear. All right, so we fast forward a little bit, and all of this is forgotten. The De Sola Price work, which appeared in Science, which is a somewhat noted journal, appeared in Science, just seems to, and it was more in bibliometrics maybe, or information sciences, wasn't quite known by everyone, or hadn't become sort of this universal famous thing. But this is when this takes off. This is actually about networks again. It's not quite the same analysis, but it's basically the same idea of Simon's model. So it's Barabasi and Albert. Raker Albert is at Penn State now. Yep, I think. And Barabasi is at Northeastern. And he's a superhero and runs a big group there. So they come up with a different term, preferential attachment. Yeah, so this happens with ideas. Often actually things get invented at the same time by different people around the world. There's lots of evidence of that, examples of that. But this sort of took a while before it was rediscovered in another context, and now we've sort of filled in the details of when people figured this out. They thought about undirected networks. So actually at Notre Dame at that point, and they were looking at the web, which this new thing had emerged, right? The web. So this is sort of 97, 98. They were doing the work. Got published in 99. So, the web is only 5 or 6 years old, so there are web pages. You think of web pages that point to each other. But they had a history of how this. I think they had a little bit of a history, but they didn't. That was too hard to look at. I know that Barabas, Reka basically had some time left at the end of her PhD, and he said, "Why don't you work on this networks thing? I've been thinking about it for quite a while. Had some false starts. Here's what you should be able to do in 6 months. Maybe just structure, dynamics of networks, and dynamics on networks. We'll just knock all that out." So structure, we've probably sorted that out. It took about 15 years as a whole community of people working. Right. Okay, so let's see. So it has this kind of problem of how do things grow. They have a growing model. Why does one node that appears, it's directed, right? So a new node appears and it points to some number of nodes that already exist, but it's pointing. So you don't get, nothing's pointing to it, so it has a size 0 problem. So we can sort of just do this +1, everyone gets a +1. But everyone's fame is how many people are pointing to them already, right? That's all, their notoriety. You can think of it in the same way. We have a fix for this, which is, it's hard to say, okay, that person has 30 people looking at them, this one, or this web page has 40, links to it, and this one has 30. You can't do that. No one's going to do that. But if you land on a random page and then look at the pages it points to, you actually, and we can come to this later on with networks, the ones that it's pointing to have this property of being well known already. So that's a way to do it. You can randomly connect to a node and then connect to some of its friends. So these are relatively less burdensome kinds of things to do. You're just going to wade in on a node, boop, and you connect to something, and then you start to kind of latch on from that. So it's a very natural kind of social thing too. So that's just a bit of a technical thing. So two pieces, I should say, okay, I guess I should highlight that word. They call it preferential attachment. It's a bit like cumulative advantage, but the attaching is preferential. And the word they used the term they used was scale-free networks. So these networks end up with the number of friends that nodes have so their degree has this distribution, right? So if you sample a node, what's the probability that has degree k has a power law size distribution. So it's the same business. So instead of instead of a group, the idea is now that your group size is how many edges come into you, which is a very natural kind of thing. So this turned out to be mathematically fun to work with, easy to work with. So this physicists just went berserk with this. Absolutely crazy. Yeah, fantastic, right? And these kinds of networks appear. There's a lot of arguing about whether the power grid really is like this, and lots of going back and forth. But certainly there are some heavy-tailed distributions. If you look at their original examples, and we'll come to it later on when we talk properly about these things. If you look at their original examples, they had the web for Notre Dame. They may have had an actor graph. I'm not sure if they did, but they had a power grid. They had the power grid, and that had a scaling exponent of 4, right? Gamma equals 4. So that's not a very powerful kind of story. And it turns out that really wasn't right. Anyway. As I said, we'll come to it later on. So the next section, which we'll start on Thursday, is about this kind of version of our model. And we have a bit of a mess, and it evolves, and there's an optimization process that cleans it up and turns it into this power law size distribution. And that's Mandelbrot's view of things. And he and Simon have this kind of terrific argument about it that's carried out in the literature. So we'll see that, and this is where we get to the Highlander story. But this is our next port of call. All right, so Simon's model is awesome, and you get to solve some little pieces associated with that. All right, very good. I'll pack up, and then we'll have, if you want, their office hours are going to be over in the other place. Thank you.